got food. Okay.
Mhm.
Just trying to let you know that the people on Zoom can't hear.
It'll be exactly 2 days until the final executive action on the border took effect. Took 3.5 years to implement, and guess what? Things at the border now getting worse. ¿A dónde vas en los Estados Unidos? California. San Francisco, ¿por qué? Tengo una familia. Y usted, señor, ¿a dónde vas en los Estados Unidos? San Diego, ¿por qué? Appreciate Coleman is live with no information on the continuing border crisis. Continue to be.
Good evening, Trey. It's unclear if or when President Biden's executive order will have any impact on the staggering number of illegal crossings at the border. CBP apprehended more than 4,000 illegal immigrants at the southern border between ports of entry just yesterday alone. Keep in mind, Biden's executive order has been in place now for nearly
Thomas, can you mute?
for illegal immigrants. So some Currently, the coalition is in Acuba, California, and witnessed migrants from all over the world illegally cross the border this morning. And they perform, they showcase their culture, their delegation, they showcase, that's like the Olympics, if you want to think about it that way. And it's huge. Change. You've never seen it before. The largest gathering of indigenous Pacific cultures, 27 nations being represented. We just talked earlier.
Somebody has the news playing in the background. If you can mute.
Reconnecting and rebuilding. So the biggest challenges of these nations. It's really is the point of this mark. As you can see, plenty of chicken skin moments today. This is going to be going on with the certification. Tomorrow, you guys, Municipal Village, open in the Hawaii Convention Center. All kinds of events, all kinds of programs. Follow our website for more information. Here stands for chicken. So much happening. You can watch it. Opening ceremony live on live and streaming live on our website and Facebook page. And checking it out. You can also find a full list of events on our website, hawaiinews.com.
People get friends who create assumptions based on appearances.
The filmmaker from Aberdeen is a common struggle for fellow teams.
Openers Now is sponsored by Installation Furniture.
Or customers that they all, so I'm looking for anyone. Something like this.
Okay.
And then I was thinking to go with it. And then to tie it together. I don't know. Yeah. Yeah.
Can you at least see the person first?
Sure. They've been talking about this week.
An official message from Medicare on call. So, don't hear that. Regularly check your Medicare claims to make sure they're back. Learn more at Medicare.gov/fraud. Thank you for the U.S. Department of Health and Human Services.
All told, I guess coming up on about 14 years. I've also done nutrient removal at treatment plants for 5, and I had a 10-year stint as a utility engineer in Florida. And ironically, it was ended up managing a septic to sewer program. We had 46,000 septic systems, and program failed after spending $20 million in engineering. And it was supposed to be a $600 million program. We had a public revolt. We had people literally coming by the thousands and complaining. And so that's where I got my feet wet. And I think I tell people to this day, it wasn't a negative. It actually kind of fueled my passion going forward, and probably why I landed at Orenco. So I thought that would be an interesting thing to talk about. So today we're going to just talk a little bit about Orenco, not a lot, just so you know who we are. And I'll introduce a couple products to you that we do, liquid only sewer and Advantex, and I'll kind of show you how that stuff works. So if you haven't heard of Orenco before, not surprised, but we're actually one of the largest privately owned family companies that is in the wastewater business. We've existed since 1981. We have about 460 employees as of today. We were actually created in Oregon with the intent of assisting small communities that needed wastewater solutions. Our founders, one was a college professor, one was a local municipal engineer, and they started the company in their basement. And so it's a really interesting history. We're probably the only company today that actually provides complete solutions to small communities, where we actually provide collection and treatment. We integrate them together, and we do a ton of business in rural America for that reason, is that we can show up and actually provide a turnkey solution. So all told, we serve, I think last count through the United States, over 300 communities, but we have on our collection side, I think we're approaching about 200,000 connections. And on our treatment side, it's hard to quantify that, but we refer to our treatment as pods, and I believe we're at about 60,000 pods in service across the United States. Very similar. We do a ton of work, not surprisingly, in coastal areas. You'll find us in Florida. You'll find us South Kent Island in Maryland. You'll find us all over Chesapeake Bay, actually. So basically anywhere that has very similar situations, a lot of times, high water tables, something that they're trying to protect, we play in those areas. The system you're proposing here is proven? Yes, definitely. No, that's all we do. Oops. So just to get you used to our lingo a little bit, so we have two really flagship products that come into play in projects like this. One is Prelos, which is our treatment system, and I'll elaborate a little bit more on that because it gets a little confusing. There's a lot of other names for these systems. And then Advantex, which is an attached growth process, and I'll explain a little bit about that, but I'll also explain how we interact with other treatment processes as well. So as you're finding out, I know it gets really confusing. So when you go into this goal of having a community wastewater system, there's a lot of options, and that's what you're finding out, right? You've got gravity collection, grinder pump systems. Prelos is a liquid only sewer, and that's what we describe it at. It's also known as effluent sewer or step systems. We try to avoid calling it a step system, and the reason being is STEP stands for septic tank effluent pump systems. And some people really get the wrong idea about these systems when they hear the word septic tank. So we've been trying to steer it away from that. There's also vacuum sewer, which really wouldn't be appropriate here as well. So those are the four main collection systems. And then in this particular instance, I've heard the word package plant. I'll explain that a little bit. You have the existing lagoons at American Water. Certainly an MBR would be an option when you start talking about nutrient removal, and I'll explain a little bit about what we do as well. It's a membrane bioreactor. So a lot of times you'll find them in areas that have a goal for highly treated water. So when you start thinking about gravity sewer and try to think about whether it makes sense or it doesn't make sense, if you're not familiar with how it works, basically you have deep buried pipes that start at about 4 feet deep, and they follow a gradient of 0.5% plus or minus down to the point where you get too deep, and then they have to put in a lift station, and then that lift station pumps it on to the treatment plant. So when you start thinking about coastal areas, and a lot of engineers haven't gotten this memo, is that it really doesn't make a lot of sense in areas with high water tables because those pipes are underwater. If you've got flood events, the whole system goes underwater. And if you've heard of the term I&I, it stands for inflow and infiltration. A large portion of your flow ends up actually being non-wastewater. And it's so beyond just the cost of building it, in an area like this where it's an elongated service area, basically you'd have at least probably, I'm going to guess anywhere from two to five lift stations along the route to make it work. I would say it just, to me, it doesn't make sense. And I'm saying that just based on my experience, that this would not be an area that I would say is conducive to gravity sewer. If you're not familiar with what some of these things are, if you haven't seen a lift station, that's a lift station over to the left. That's typically what they look like. It's a wet well that can be anywhere from 20 to 30 feet deep. You've got a control panel, odor control. It's got telemetry. It's pretty major infrastructure. And of course, if you're going to a conventional treatment plant, they can be pretty robust as well and take up a lot of area. So throwing that out there, that's not what we do. So I'll explain what we do. You heard about grinder pumps today. So biggest difference between us, and I'll show what we do, but a grinder pump basically is intended to pump all of the wastewater. So that sounds pretty good, right? Because I'm going to tell you, we're going to leave part of that wastewater in the tank. So that might sound a little bit odd. So a grinder pump basically is going to, it has an auger, and it's almost like your disposal system in your sink for your food. It grinds up the waste, creates a slurry, and then pushes it out in the main. So great, all the wastewater leaves the system. The couple of things to do that, you need a much more robust pump than what I'm going to show you. So the pump weighs over 100 pounds. The other thing is it's a very expensive pump. So it's not uncommon for grinder pumps to be anywhere from $2,000 to more than $3,000 to replace. It takes a couple of people to take them out of the pit. They're typically 230 volt 230 volt service is required. And here's the most important element of it. As soon as you put solids out into a pressure pipe, you have to maintain a certain flow velocity because you're pumping solids. So that means that when we size the mains, you have to maintain 2 feet per second to keep those solids moving till they get to the point of discharge. So that certainly causes some issues when you have a long pumping distance like you have here, and I'll show you why that makes sense. But essentially that means you're probably going to end up with lift stations still, because you can only pump so far before you actually have to repump it so you can maintain that velocity, because I can't make pipes bigger because then I'm going to get sediments falling out in the pipe. The other thing is it's higher strength wastewater. So I'm going to show you the difference in our system is that we're actually providing, it's the only system that actually provides primary treatment in addition to collecting it. So not only do you get higher strength wastewater, because you're putting it into a slurry, it's actually harder to treat and it's actually stronger than wastewater from a gravity system. So a little bit different. So good question. So yeah, please stop me because I'll have a tendency to geek out and talk at a high level. So sure. So the question was, what does higher strength organic waste mean? So when we describe wastewater, we use a term that referred to as BOD, and that stands for biological oxygen demand. So essentially to break down organic strength in wastewater, use oxygen. So if you're familiar with an ATU, that's what they do. They have a tank and it blows a lot of air in it. That's essentially what it's doing, is it's breaking down that BOD. So when I say it's a higher strength wastewater, that means that BOD is at a much higher level than our system. So it takes more oxygen to get rid of it. So it just, I think that's, I don't know, does that make sense or? Okay.
It's bad, and lower strength wastewater is better.
It's easier to treat and it's easier to pump. Yeah. Yeah. So to kind of circle back now on Prelo sewer and why is it different again? So this isn't new technology. A lot of times people hear this and they think this is something that's new on the market. It's just, it's evolving. It's been evolving for the whole 40 years we've been doing it. Interestingly, I actually wrote an article about this. It dates back to the 1970s in Florida, first commercial systems, and they were referred to as STEP or septic tank effluent pumps. Those systems still exist today and still operate today. So not new technology. It's been over 50 years in the United States in community-based systems. Prior to that, the concepts date back into Australia and, believe it or not, Africa, dating back into the 50s. So the concept's been around for a little while. The first commercialized systems, or not commercialized, the first community systems materialized in Florida in the 70s. Orenco was the first company to commercialize it in 1981. So we've been doing it for over 40 years, 41 years. So the concept's pretty simple, is that when we take wastewater from the source, be it a home or a commercial property, you provide a tank that's big enough to keep the flow there for a certain amount of time. So we typically, our smallest tank is usually 1,000 gallons. We also use a 1,500 gallon tank. And the cutoff point is we'll use 1,000 up to 4 bedrooms. Above 4 bedrooms, we go to a 1,500 gallon tank. And then commercial, we size things on a case by case basis. What that means is we're creating typically around 5 days of retention time in that tank, meaning that when the wastewater comes in, it on average stays there for 5 days. Over those 5 days, what happens is you can see in this drawing here is that the solids settle to the bottom. Scum is going to go to the top, and you get this clear zone in the middle of the tank. And this happens naturally. It doesn't require aeration. It doesn't require energy. It just happens because you have a tank big enough to keep the flow there for long enough. So when you hear the word septic tank effluent pump system or step, guess what your septic tank does? Same thing. It's just usually a little bit smaller tank than we're using. So what's different versus your septic tank is this pump vault right here. You can see here, it's designed just to take that wastewater only out of that clear zone. It has a little intake on the bottom of it. Wastewater comes in from that clear zone and it enters through a filter. Believe it or not, there's a large filter in there with 1/8 inch openings. And then it goes into a pump. And the way I would describe that pump, I have a blow up of it here in a second. It's similar to a well pump. So if you have a water well and you pull the pump out, it looks like same as a well pump. Reason being is we know well pumps last for a long time, really robust. They've been around for a long time, except it's a pump that mirrors what a well pump is, but it's designed for wastewater applications. So why do we do that? When it ejects out of here, then we can put it out into a collection system. And it's a very powerful combination. So I don't have solids in there. So there it is connected to the pressure main. And I have this really powerful pump. And again, I'm going to try not to geek out, but so we describe pump power in terms of total dynamic head. What that means is if you hook a pump up to a pipe and you start extending that pipe straight up in the air, how high in the air can that pump to? These pumps can pump 230 feet high. So I can put a pipe straight up in the air 230 feet. So the combination of not having solids and having this really powerful pump, it gives me this, basically what it creates is a water system, not a wastewater system. So when you look at that collection main out there, there's no solids in it. I basically have a water system. So I always tell engineers when you design this, think like a water system, not like a wastewater system. So I can loop lines, I can pump huge distances, because remember I said that the difficulty in a grinder pump system is solids want to settle if I don't move them. I don't have to worry about that. Guess where the solids are? They're in the tank. So I can pump huge distances without any need for other lift stations. So the only restriction really in an area where the topography is fairly flat is just how much friction I lose in the pipe and how much hill I have to overcome, which we refer to as static pressure, meaning that if I'm pumping here in the elevations 10 feet and I'm pumping to a treatment plant that it's 100 feet, that means I have to overcome 90 feet of static head to get to that hill. But I can control how much friction loss I have in that pipe. So I can make pipes bigger so that I don't lose pressure in the pipe. And I can extend pumping distances, huge distance. So we have systems that pump 10 miles without any intermediate pump. If I do have to repump it, I can do it with an inline pump. I don't need a wet well to repump it. Basically, I just put an inline pump to boost the pressure. That's all it is. So we actually have a system, South Ken Island in Maryland, where the long-term plan, because we have 8,000 connections in the first phase, the long-term plan is to double that capacity just by putting an inline booster pump at some time in the future. We're actually going to double the capacity of the whole service area. So it's a really cool tool that you can apply. So now you can see this collection main out here. So it's left the on-site unit, goes out to this collection main. That main is typically 2-inch diameter, but again, we'll make that main bigger to reduce the pressure losses. It can go uphill, it can go downhill, it can deflect around anything you need, because let's say you're going down the right of way and I run into that brand new water main and a fire hydrant. Well, I might be at the same elevation. Well, this thing can gradually deflect underneath it and avoid it. I don't have any fittings. It's just polyethylene pipe. I'm just steering it wherever I need to do. Yeah.
The baby question.
Sure.
Does each house have its own tank?
So generally, yes.
The question.
So the question is, does each home have to have its own system? So in dense areas, we will do shared tanks, or what we call as clustering, where we'll bring multiple homes to a single tank. Here, that doesn't make sense. They're basically wherever your cesspool is or your existing septic tank, this unit would go in proximity to that.
What happens to all the solid waste?
So great question. So the question is, what happens to the solid waste? So it's staying here in the tank, right? And if you're familiar with septic systems, you'll say, well, I pump my septic tank every 3 years, 4 years, 5 years. That's typically a regulated number. And the reason being that if you have it on a septic system where you have a drain field behind it, the regulators have to look at the worst case situation, right? You could have 6 people, 7 people in that home, and they want to make sure that you never get solids. The solids that are in the tank, they want to make sure it never gets out into your drain field, because that will make your drain field fail. So they pick an artificially low number. So in these systems, we're visiting them every 3 to 5 years. We're measuring that scum and we're measuring that sludge. And the objective is you want to keep it there for as long as you can, because in factuality, if you were doing that with your septic tank, you can prolong that period out because it actually becomes more efficient with time. So these are designed to keep the solids there 10 to 12 years. So the pumps, and I'll get into a little more detail, but the pumps are actually the most robust part of this system. So I'll show you more detail. The pump actually has 2 components to it. So there's a motor. Actually, hold that question. I'll show you in a graph. It'll make more sense in a second. All right. So again, here, small diameter mains, shallow bury. Typically, they're 3 feet. They can be shallower if they need to be. Flow can go either direction. So you can actually have multiple places of discharge too, long-term. You could go to a treatment plant. You might have something local. It doesn't have to go to the same place. You can actually have reuse. Let's say I had a park here. That's a park and I actually want to do reuse there. I can actually pull off of the system and do treatment local to that, because the system doesn't care where I pull off from. It's just like your water system again, right? So it's a very flexible system. You can use trenchless insulation. So for those that don't know what directional boring is, I can at least give you an introduction to that too. So kind of going back to what's the difference between the grinder and the Prello. So here's an interesting picture. This gives you a scale of what a pump looks like that handles solids and one that doesn't. So the one on the left here, that is a grinder pump. The one on the right, that is an effluent pump. One on the left weighs over 100 pounds. The one on the right weighs about 30 pounds. This is where the difference comes in and why there's a difference in cost. So the life cycle cost on the bottom, if you're not familiar with life cycle costing, kind of think about your car if it makes it easier. You buy a car, and guess what? It's under warranty for the first few years. You have nothing to worry about, right? Your car works great. You just change the oil. Everything's wonderful. As your car ages, right, things start to deteriorate. You replace tires, you replace wipers. The cost of operating your car goes up. It's like that with wastewater systems as well. But you replace those parts and you restore the system to fairly new condition, and it still does what it's supposed to do. As the systems age even further, you start to get into big components. So in the case of these 2 systems, the big components are the pumps. Ultimately, if you look at grinder pump literature, they usually say 15 years, 20 years for life cycle cost on a pump. $3,000 pump, you can start to do some math, what the cost is per year and what that liability is. Pump on the right, it's rebuildable in about 5 minutes. It is 1/3 of the cost of a grinder pump to replace the whole pump, but again, it's rebuildable. So I'll show you what that means in a second. So typically the O&M costs on a liquid only sewer system average out on a mature system to about $100 a year. So that's when the systems get up here where they've aged. It's usually 2 to 3 times that for a grinder pump because of the cost of the pump. That's the difference maker. So this is the pump I'm talking about and why it makes sense. So the best way I would describe this is the bottom of this is a motor. The liquid goes in the middle. So again, this is the liquid that doesn't have solids in it. In the top is an impeller stack, and you can see a cutaway here. And as the liquid comes in, it goes up through this impeller stack, and that's how it generates this pressure. So the motor end averages about 40 years between failures. It is actually, you would think the motor would be something you have to worry about. Motor is the most robust part of this pump. We just don't see a lot of motor failures. The liquid end, this part here, that impeller stack lasts about 30 years. And either the liquid end or the motor end can be replaced in about 5 minutes. You don't have to replace the whole pump. It's 4 screws. You replace just the motor, or you just replace the impeller. An impeller stack right now is about $170, and a motor is about $450. So when we start thinking about why the economics make more sense in these systems, it's the fact that the pump is rebuildable. It's the fact that it doesn't take much work to do and very lightweight. This is where the economics of the system start to come together. We believe in it enough that we actually warranty these pumps for 10 years. And our warranty rate is like 0.1%.
What fuels the pump?
What's that?
What fuels the pump?
It's electric. It's a 120 volt single phase service. So the Prelos unit itself is made from DCPD. You can see here, this is what 600 Prelos units looks like when they're staged for a project in Alabama. Typically what we do, especially in Hawaii, was we would put it into a shipping container. In halves. We have a business partner here that would assemble those tanks locally and then make them available as complete units when they get installed. So here you can see a unit being installed. If you're trying to get dimensions on that, it's about 7.5 feet across, about 6 feet high, and that riser is typically 24 inches. It goes on top. So when it's finished, this is what you see, is the access on the riser. So that's it here. So this is all buried. And here's a control panel that controls the system.
Got a lot of high water here.
Mhm.
You know, what's the strategy? Just popping out of the ground?
So that's what the 2-foot riser is for. So the question is, what keeps this coming out of the ground? So just like a boat, right? You put this in water, it wants to float. So the way you combat that is what you put on top of this tank. And in this case, what is combating the buoyancy is actually the soil itself. What's that?
I just put it in a septic system.
So,
It had to be based in cement.
so you can.
Then-
So hear me out though. So that's why this 2-foot riser is significant. So if you run the buoyancy calculation, we're looking for a factor of safety against it floating above 1. So what we do is if this riser is less than 2 feet, that overburden of soil isn't enough to get it over 1. So we can do that. We can make this 1 foot. Then what we would have to do is put a concrete ring around the midpoint of the tank. As long as we have a 2-foot riser, there's enough soil there to resist buoyancy. So what happens, even these get installed in water all over the country. What they do is they'll excavate this out, kind of like this. They'll put usually a clear rock in the bottom of what we call as a Kelly well to pump all the water out while they're installing it. They'll set the tank and then immediately they're going to put water in that tank to stabilize it. Then they backfill it. This gets compacted above the haunches. This overburden covers the whole tank. And the overburden also includes what's over this midpoint seam. And it actually includes an angle of about 45 degrees coming out from the tank. So that weight is actually pretty substantial. So that's basically, if you read our literature, we say, as long as you got a 2-foot riser, you're good. If you're less than that, put a concrete ring around the midpoint of the tank. Yes.
So kind of seeing trees, but I'm not really seeing forests.
Okay.
Pumping water where, then what do we do with it?
So to back up, I guess. So the question is, what do we do with the water? So I mentioned that the water gets out in this collection system, right? This is what we're manifolding all these systems. All the homes have one of these units. They all tie into a collection main. From there, that's the main that's going to that treatment plant, that lagoon system, and it discharges there. No, it's the American Water one. If that's what we're using, it can go to our treatment plant. If you want to do treatment locally, that is a decision in the community, right? You could provide local treatment, but as was correctly stated, is the difficulty in a treatment plant isn't just treating it, it's also what do you do with the water. So it's not just providing treatment, you have to figure out what you're going to do to discharge it afterwards. So that's one of the advantages to going up to the American Water plant, is that they already have some of that available to them. They have the well, which they need to get rid of, but they also have opportunities for reclaiming the water and using it, say, in a golf course, especially with higher level treatment.
Well, that's what I was saying at the beginning, is that American Waters and Monolani are in active discussions. American Waters and Monolani used to do just this, just that. They used to water their nursery with it. And then when they got out of the nursery business, they said, well, no, we don't want to do that anymore. But the new owners are open to that, to the reuse. They're even talking about creating a fire break between the highway and the resort to protect from fires like what happened at Mauna Kea.
And by the way, Torres and the governor approved the grant exactly 2 years ago, not 5 years ago, 2 years ago, exactly 2022, when the money was approved. But American Water was, hey, we're a business. Show me an economic reason why we should do this. Have we done that?
Again, that's the analysis that American Waters is doing right now, because they know that at some point their use of injection wells is going to be shut down. So that's what they're discussing. That's what they're working with the Mauna Lani for. But I think the key here with Mike, and correct me if I'm wrong, Mike, is that your system can take, collection system can take the waste to any number of types of plants.
Absolutely.
It doesn't have to be yours or American Waters, or we can go anywhere.
Yeah, and maybe, I mean, to put a little bit different perspective on the existing facility too, it's kind of interesting, and maybe the original permit said this, is usually injection wells are secondary to a primary disposal, meaning that when it was developed, if they were growing sod, that was their primary disposal. And when it went away, they really probably should have been regulated to upgrade their plant and not just rely on the injection well. They should have been able to replace the reuse part of it. It's kind of interesting. I mean, they have that golf course there. It would make sense that they would actually see water as a resource and want to put it on the golf course too. So I don't know where they are with that, but I would think that the reason they're not doing that right now is that plant is, by technology standards, a lagoon plant is like way down here relative to where technology is today, as far as providing higher level treatment. So I'm sure that's the catch is, well, do they have to upgrade their plant to actually go to, you know, really the proper reuse would be to put it on the golf course. So if you're not familiar with directional boring, this is used pretty extensively with these systems. So best way I would describe it, it's like drilling a well horizontally. It's instead of vertically. So what happens, this is a directional boring right here, these two. It drills pipe down the street, and usually about every 400 feet, they'll exit, and you can see, you know, there's an exit hole at the bottom. They'll pull the polyethylene pipe back in place, and the bigger the rig, the further they can go. And the pipe, this is what it looks like. This is actually in Vero Beach, Florida. That's the sewer pipe on a roll there. So there's no joints, no fittings. They simply just pull it all the way back, and it's kind of nice. It becomes watertight. There's nothing to break there. But that gives you an idea. So when the soils allow for it, if you don't have rock, that's a great way to avoid certainly putting in open trenches. And as you saw with the water main going in, I'm sure it was pretty disruptive even for that, for cutting the road and putting that pipe in. Yeah. Go ahead.
Sorry, I'm gonna ask. You say
Sure.
you don't have rock. What if you do have rock?
So there's options there too. So, and it becomes really a cost risk. The question is, well, what if you do have rock? Depending on the rock, they can put diamond bits on the end of these and sometimes bore through the rock, but certainly volcanic rock is not the best to be trying to drill through. At that point, really the fallback is just to put a trench in. It's usually the most economical way to do it. The nice thing here too is you don't have to get down to 3 feet if you're riding rock. You can arm the top of it, you know, put a concrete slab or actually shallow the pipe up if you have to as well. So the other thing that's more interesting here, so I was actually, when I was driving in yesterday, I was stopping and taking some pictures. So I took those pictures yesterday. So yeah, I remember when George had mentioned that they were putting in new water mains, and right away I was like, wow, what are they doing with the old water main? So one of the neat things, because we don't have solids, we don't care so much about that running line and going up and down and problems. So you can see the new water line is, here it is right here. Of course, you're all familiar with it. You can see it going down the road. The old water line's on the other side. So you can see these yellow valve pits. Usually that's just pretty close to the T on where the old water line is. So that water line could be a conduit for this type of system. So there's a process called slip lining. You can see a polyethylene pipe being pulled into a conduit of some sort above it. That is certainly on the table. And I talked to a contractor just to find out what that means. It would cut the capital cost in about half to slip line versus doing some other method. So certainly that would be a really cool way to execute this project. And it actually works out pretty well because you have to have separation from the water line. Well, it would be, it's on the other side of the road. So I think that would be a really cool alternative to project delivery on this. Yes?
So what is this pipe made of? How? Critters,
Absolutely.
trees,
So the question is, what is this pipe made of? So you can see that pipe there with the two stripes on it. That's high density polyethylene. So basically that pipe is rated by pressure. So the typical pipe that's used in our wastewater systems is usually rated for 160 to 200 PSI, and we run it at about 40. So it's a really robust pipe. Again, there's no joints. Yeah, no critters can't, the wall thickness on is very thick, very heavy. No, it's a commercial, it's not a garden hose, it's a commercial grade flexible pipe. So I mentioned, your question earlier was about organic strength. What was I talking about? Wastewater strength. So this gives you a little bit of an idea. So the top one is liquid only sewer, effluent sewer. So that term BOD that I used, the BOD in this system is about 140 milligrams per liter. So that's a lab test, again, where they see how much oxygen it takes to remove that BOD. Gravity sewer systems are kind of interesting. If you have a watertight gravity sewer system, or you don't have a lot of I&I coming into it, inflow and infiltration, it can be fairly strong, 450 milligrams per liter BOD. So about 3 times as strong. What you see in a lot of gravity systems, though, is it lets water in and it dilutes it. So the wastewater strength is lower, but you're dealing with more flow. So when you start designing a wastewater plant, the problem is you got to design for both those situations. You have to design for periods of higher strength wastewater. You have to design for periods of extra water. So that's one of the problems. The plants get bigger. So the grinder pump system down at the bottom again, so it doesn't have I&I, just like ours. It's a sealed system. They use polyethylene pipe, but you can see the wastewater strength is about 3 times the rate. So what does that mean? I'll show you. It really, beyond just the solid settling, there's actually other benefits to actually having partial treatment already occurring. So this, I just figured I'd pick an MBR plant. So if you're not familiar with what an MBR plant looks like. So on the left, wastewater comes in there. That's a pre-anoxic tank. It's where the wastewater enters in and it equalizes flow. Then this little contraption up here is actually a filter, or a screen process. So all of the inorganic stuff actually gets removed there and put into bins. Then it goes into aeration basins. So these are aerators, blowers, that pump air into this tank. So remember I talked about the significance of that organic strength. Well, it takes air to remove it. That's what does it, those blowers. So they got very big blowers because they're pumping this air into that system to reduce the organics. The last system there, they have these cassettes of membranes. And that's the final treatment in this treatment process. So I'm sure you've heard it. This would be something that would be on the table for a system like this. It does a very good job of treating wastewater. So if you're using grinder or if you're using gravity sewer systems, you need certain size blowers, you need certain amount of these screens to get rid of inorganics. Guess what happens when you put a liquid only sewer on this? So that first one where it says number 1, that screen, we call them headworks, you don't need it. And at most, it might be a very fine screen for the MBR. It goes away because in the collection system, I already have a screen in there of 1/8 inch openings. The collection system actually takes care of that. So that piece actually goes away. Number 2, that's on those blowers that's pumping air all the time. Well, guess what? Because the organic strength is about 1/3 the strength, I don't need as much oxygen, they get smaller. Number 3 is that tank out in front. So that's actually for solids handling as well. There's 80% less solids because guess where the solids are? They're in those tanks at each property. So reduces the solids at the treatment plant about 80%. And then generally all the tanks get smaller. There's no I&I. We don't need as much aeration. So it shrinks the plant down. And really the big takeaway here is this is the only collection system that actually creates that economic benefit on the treatment side. So when you're talking about Do I do grinder pumps or do I do a liquid only sewer? Understand that it's not, don't just compare the collection systems. You want to compare the integrated process. Because the treatment system here, when you talk to an MBR company, they'll say, guess what? If I design for this wastewater, the plant's going to get smaller and cheaper. That all makes sense? So it's the only collection system that actually provides that benefit. So what about on an existing lagoon? Well, some of the same things apply. We don't need pre-treatment. It's already been pre-treated. So if you were taking grinder waste into this, for example, or if you're taking gravity sewer, they're designed this, when they look back at how it's going to impact this, they're looking at more solids accumulation. They're looking at maybe having to have headworks, maybe more lagoons for treatment or more tankage. So again, there's definitely a benefit to using a system that already has pre-treatment in it. So one of the neat things here too is, and I'm not really clear on how the wastewater comes in here. This is not a high-tech system. These are what we refer to as facultative lagoons, but I'm going to assume somewhere in here there's some screening. This pipe could be dedicated and bypass all that. So if they're looking at upgrades, even this, so an upgrade on a lagoon might include adding aeration into it. It might be adding more infrastructure to it, like headworks, or polishing on the backside where they actually add, even our technology gets added on the end of lagoons. The impact will be different. And in the eyes of American Water, when they actually get down and analyze this, they should see it as a favorable option if they're looking at upgrading that plant. So again, there's some value there. What do we do? So we actually design treatment systems that take advantage of this treatment already happening. So this is an attached growth process, all modular. So what that means, if you get used to our language, we refer to these as pods. And we simply add pods to get to whatever capacity we need. So those vessels you see there, about 42 feet long, 7.5 feet across. And essentially wastewater comes in there. We don't have any blowers. So this the reason I put this up here is it demonstrates the difference in that a wastewater can make. There's no blowers on this system. So if I'm putting a system in proximity to buildings that don't really want a treatment plant, this has no open tanks, no blowers. It's just a series of recirculating pumps that actually load a bed of media that's made out of textile, and the textile is the host of the microorganisms that break down the wastewater. Very low energy, very simple to build, very simple to maintain. So it doesn't require a lot of operational changes. Capital cost is going to be higher on this versus an aerated system. So it's usually in the range of 1.5 to 2 times higher on the capital cost, but 1/10 the cost to operate. So you actually have to do the life cycle cost to see if it makes sense. What do these look like when they're finished? Well, there's some examples. This is a pretty good example here. This is actually a nitrogen removing system in the left. So when those tanks get buried, that's what they see above ground. They can be completely above ground. They can be completely buried. They can be half buried. So just again, throw it out there. It is an option that could be, but again, that's just the treatment. You still got to figure out, are you reusing it? How are you disposing of it? So just to kind of look what this looks like in Puuko. So as I mentioned, the difficulty here is it's a long service area. So it's, when you start to think about gravity only tends to work when you have high density and you can put the lift station in the middle of a service area. In an elongated area like this, what that means is that every time I get too deep, I got to put a lift station in, and I can only go so much out each direction. So not only am I running gravity sewer, I'm running that pressure pipe to collect all these lift stations as well. If you're downstream towards the ocean, you might not have enough fall to get into a gravity sewer, even at 4 feet, because you got to plumb from wherever your stub out is on your home, get out to the roadway, and hopefully that stub out that they gave you at the street is deep enough that you can get into it. Not always the case. So you might need a pump anyway. So really an interesting example. So all of, the demographics of Puuko, I always kind of check this to make sure that it makes sense with our type of system. 2.25 people per household. Again, that actually suggests that pump out intervals on the tanks is very manageable. There is a build out population, meaning that there's property undeveloped. Systems very easy to connect into. It's just like a water system. When somebody connects into a water system, they provide a tap. Somebody gets water service. Same thing on this. You provide a tap, you extend it to the new property. The other, I guess the important thing here is there's a mix of septic systems, ATUs, cesspools. I also suggest, when we think about phasing, a lot of people think about phasing the properties in front of the home. And I always say, well, the difference in these is if you're limited financially, just get the lines in the ground. You can actually phase this based on priorities for connecting. If you want to connect the cesspools first, you can. If you want to defer the ATUs to the end, you can. And the argument for deferring ATUs is people have put an investment in them. And a lot of people get a little upset to say, hey, I spent $50,000 and you're telling me to take it offline. So you can. The question is, why would you want to? I mean, you're running a blower all the time. So there's no advantage to keeping that blower operating. And so you actually raised one interesting question though. Can we reuse other tanks? So I've shown you what a Prelos tank looks like. You can. So if you have an adequately sized tank that's structurally sound and watertight, we actually make adapter kits to put the pump vaults into that tank. Now, does that make sense? I often say don't get too excited about it. The reason being, to evaluate that tank can cost you X amount of dollars. The incremental cost to go up to a brand new tank sometimes suggests it's just better to replace it. But if you have a lot of confidence that those tanks, that a large portion of those tanks are usable, that is an option. Yes.
Actually, we've learned in the last few years that BTUs, they treat the wastewater to a higher level than a cesspool or a septic, but there's still stuff going out in the leach field. So it actually could be a benefit if it was.
So an ATU is kind of so if your end goal, so what you're really trying to keep away from the reef is probably nitrate and BOD. So ATUs will get rid of BOD pretty effectively. The hiccup is that because it's just an aerated system, nitrogen goes through a cycle. So when it leaves a home, it's in the form of ammonia and ammonium. When you aerate it, it becomes nitrate. If you don't add extra infrastructure to convert the nitrate to nitrous oxide, because that's the next step in the process, guess what? You're just discharging nitrate. So an ATU is kind of an incomplete system in coastal areas because you're still putting that nitrate out. But again, I don't think when you're taking it somewhere else that presumably is putting all the flow in one place where you can actually take that next step and convert nitrate to nitrous oxide. And if you're not familiar with that process called denitrification, it really doesn't make any sense. Yeah, we'd be already doing ammonia to nitrate, but the plant would be designed to do that anyway. So, yes. So there is. So there's two floats in there. So the question is, what turns the pump on? So in the top of that system, there's two floats. So the bottom float is the float that activates the pump. So when the liquid level gets up to a certain level, it triggers that float and tells the pump to turn on. If it doesn't turn on and it goes up to the second float, that is the alarm float. So it'll say, hey, that first float didn't do what it's supposed to do. It will actually say, I got a problem, and it will activate an audible and a visual alarm at the panel, meaning you're going to hear it, you're going to see it. That second float will also try to turn the pump on again. So if the problem was that first float, the second float is actually going to turn the pump on, and you'll get this intermittent alarm each time. It's going to get up there, it's going to alarm, but it's still going to turn it on. We actually have a more advanced panel that learns what you normally do, and it provides another level in that it knows what it's supposed to be doing based on your history. And if it's not doing that, it actually has a PLC in there that will try to turn the pump on. But I don't usually recommend that. It's an added cost and added maintenance. And honestly, these systems are robust enough and the failure rate's so low that in my mind, it never makes sense to take that next step. So that's how the pumps get turned on. Just to kind of give visual, so I deal with this all over the country, and you've heard about rising sea levels and whatnot, but I just want to put this graph out just to show what the reality of the problem is that whether it be a cesspool or a septic tank, if you don't have at least 2 feet of buffer between the water table, and that's the high water table and not the low, it's the highest water table, there's just not enough unsaturated soil to provide that extra treatment. whether that be an ATU, whether that be a septic system, and certainly a cesspool is going right into that water. So we see this all over the country, and this is why we do quite a bit of work in coastal areas. So we start to look at, well, what's required here. The line fronting the property, obviously low elevation, water table right there. It's relatively flat except for the north end of the route. But after that, it's relatively flat, which I'm sure you all know. The existing right-of-ways, fairly narrow, but again, we're only putting 2-inch pipe in. Again, if we're using that existing water line, certainly seems to make things very viable. But these are right-of-ways that we go down all the time. And we'll do this. So here's what the line looks like. So I came out with about 17,000 lineal feet of 2- and 4-inch pipe to front the properties. And likely the biggest pipe would be 4-inch. I can't put definitive numbers on this because I still don't know exactly where you're going to go with the line. So essentially, when we design the hydraulics, we can assume any discharge point you want. So even if that discharge point was, let's say you want to go to this plant now, but you think the line could extend north and tie into something else in the future, we can design for that. We can design, unlike a grinder pump system, we can design for whatever circumstance you want. That sounds pretty wild, but we do it. We actually put large systems into a modeling program, and we'll hydraulically model the whole thing for all these different circumstances and make sure that the pipe sizing accommodates every circumstance you could imagine.
So your 17,000 feet goes to a wide area.
Yeah. Yeah, and honestly, I just put that in, but it can terminate wherever you want. As far as tie-in routes, George and I were talking about this before. Again, we have complete flexibility here, so it can take a cross-country route to the plant, whatever you want. We can also go into the existing resort community and tie in on those existing pipes. And we have different ways to tie into that. We don't have to go into a lift station. We can tie right into pressure pipes there as well. And typically what we'll do there is a check valve. Just reminded me, I forgot to talk about the check valves too. One of the questions was, how many check valves do we have? So on the discharge, we have 3. There's one in the pump, one at the top of the pump. It's what we call as a hanging discharge assembly. And then there's one at the connection to the main. But we would do the same thing here when we connect into an existing gravity collection system into the force main. We would actually put a large check valve in that place as well. One of the interesting things that you'd have to overcome, I know in the PER, and this is what I see across Hawaii, is they overstate the flows all the time. The design flows don't make sense. And there's a couple of things that we see a lot. So a lot of design flows are based in on-site regulations where they want to be really conservative. That's okay. The other thing that happens is because of gravity sewer, a lot of design flows include that I talked about. So we're designed to be watertight. So right away, we take that I off the equation. The other thing that's happening is more and more homes have low flow toilets. And so we actually see consumptive water use going down. And I would say that the overwhelming number of our systems usually are about 150 gallons a day per household, and we see them down as low as 130. And the reason that's important is when you start talking about capacity, whether it be in another plant or if you're building a plant, the PER said 50,000 gallons. I think it's under 30,000. The best way to confirm that is get water use records. If you can go through and actually, even if you just take a sampling of your membership.
That's hard.
So they don't put irrigation meters on at all? Yeah. So that's a shame, because I know in the utility I was with, there was a lot of irrigation. We allowed irrigation meters, so you didn't have to pay for. Yeah. Okay. Well, and probably because you don't have wastewater, because once you have wastewater, you don't want to be paying double. So that's a big issue, is you probably want to make sure that they think about letting you use irrigation meters and taking that off. If people don't have irrigation, maybe you can do a sampling of those and try to figure out what the typical water usage is. Just off, if you were to connect in near the resort, it's less than 5,000 feet of pipe. Pipe probably would be a little bigger than 2-inch, probably at least a 4-inch, again, to minimize that friction loss and get the tie-in. Again, I don't know for sure, because I would actually need the utility to let me know what that entry pressure is, because I have to overcome the pressure that's already in that line. would add about 111 gallons a minute to their flow. So and we'd be happy to talk to the utility. That's what they'd be evaluating. We've done some where we actually have modeled it from the tie-in location all the way back for them, just to confirm that the concept would work. But obviously there's still some questions there on capacity, level of treatment and whatnot. But fundamentally, just getting the wastewater away from the ocean and uphill is a benefit all in itself. Yep.
Related to the fourth point there, now that we've actually made, in our previous presentation, we talked about how, even if you had all the ATUs, it only reduce, up to a certain percentage of each, mostly nitrogen.
Right.
So
It's just reducing ammonia. Right.
Right. So the question is, how does this system rate?
So the collection system, sure. So
Repeat the question.
the question is, how does this system compare? So the treatment isn't ours, so I can't really speak to that. So the collection system doesn't reduce any nitrogen. It's just collecting that ammonia. And nitrogen is really, just look at it as a mass balance. A lot of treatment processes will reduce ammonia or nitrogen in a consumptive way, but the collection system doesn't and all that. All it's taking is that nitrogen in the form of ammonia and getting it somewhere. So it becomes really a factor of what's happening at that plant. Is that plant designed now to take that ammonia, convert it to nitrate? Facultative lagoons don't really do that because there's no aeration. So that's what I'm saying. I'm just looking at the aerials. That's a question for them to answer, but I'm going to guess that it's not really designed for nitrogen removal. And what you're going to see in a plant that's really designed to complete the whole thing, and I'll speak to our technology. So our technology can be a single stage, and we're going to reduce nitrogen about 60% in a single stage system. It aerates, it does a little bit of denitrification. It'll get rid of 60% of total nitrogen, and it will get rid of about over 80 to 90% of ammonia. When you say, hey, Mike, I want a total nitrogen system, I want nitrate gone, my single stage system becomes a 4-stage system and the cost doubles. And the reason being is I have to add these other stages into the system to do, so we aerate. So when we aerate, we get rid of, I don't have blowers, but that media actually is an aerobic process. So it does the same as aeration. I have to follow that up with another stage, essential aeration, because I want to make sure that every milligram of that ammonia gets converted to nitrate. I don't want to leave any ammonia. So we actually run it through 2 stages to make sure that we do all that conversion. The next stage is actually that conversion I talked about, where I take nitrate, convert it to nitrous oxide. So the problem is that process is completely the opposite of the first stage. So that ATU, if an ATU is going to denitrify, I'd have to follow it up with another tank that has no oxygen in it. So you go from this oxygen-rich environment to an environment that has no oxygen in it. And even at that, I still can't really achieve like a super low number. Like I would call 10 milligrams per liter a low number. So then we add another tank in front. So we actually recirculate some of it back to the front, and we take advantage of the BOD coming in, because I need BOD now. I've gotten rid of it all, but I actually need some to denitrify. So I know I'm really going a little geek here, but point is that it's a very involved process. And so it's a big jump, and a big jump in cost, a big jump in technology to go from just a baseline system to go to something that's actually taking all the nitrogen out. Yes.
Have you dimensionalized costs for the baseline system?
I have, yes. I've looked at it. Sure. I think I have a slide at the end. I think I've got it turned off, but I'll bring it up. So we talked about to the resort. If I was going to tie in directly across, I came up with about 11,500 feet of pipe. Again, the goal would be to do it without any lift stations, and to make sure that I have flow there, or capacity there. So actually it is turned on here. So this is just a back of the napkin calculation. So don't take it for as absolute. And there's obviously a range here. So this gives you an idea. So that 60% total nitrogen removal, and this is just our technology, but the same things apply to other technologies. They still need the same sequence of tanks to do what I'm talking about. That 60% total nitrogen removal, that is a single stage system in our book. 30,000 gallons capacity, be about $1.5 to $2.5 million. If you were to do it with an MBR, I'm going to suggest that it's under $1 million. Okay, so remember I said some of those technologies are going to have cheaper capital costs, but a much higher and more intensive operating costs. So you can weigh both of those. But if I take that same plant, that 30,000 gallon plant, and I target 10 milligrams per liter total nitrogen. So that means is I'm getting rid of all the ammonia and I'm getting nitrate down below a very low number. There's actually a portion of that total nitrogen you can't get rid of. It's organic nitrogen. It's usually about 1.5 to 3 milligrams per liter. So I actually have to get that ammonia and that nitrate out of there to get down below a 10, which is really the threshold for small systems. You can see that doubles the cost.
But this doesn't include the-
Disposal doesn't include this.
the pumps at the homes
It does not, no.
and the cost of the pump at the home, roughly.
So the installed cost is probably in the range of 15,000 to 20,000, and it's highly variable depending on what you're dealing with there. Yep. And this Hawaiian costs, and I'm not an expert on what it costs in Hawaii. It's double what I'm used to on the mainland. Yeah. But anyways, it gives you an idea, and you can have, reason I put that up there is you can have that same conversation with any treatment company, because it's really important to probably work with the regulators to find out what your target is. And obviously the further you get away from the ocean, there will be some level of soil treatment. So it may not be as important to get down to that 10 total nitrogen or down to a 10 nitrate. I'm not the expert on that, and maybe the people at the University of Hawaii can provide more answers. Well, how far back do you got to get before you can be confident that that nitrogen isn't reaching the ocean? And obviously your goal is, if you're doing all this, you want to make sure that you address that. Yes.
Yeah, I heard the terms, primary treatment, secondary, tertiary. How does that relate to what you're talking about?
So in our case, that on-site, sure.
Sure. Yeah. The question was, we hear about the terms, primary treatment, secondary, and tertiary, and I was wondering how that relates to exactly what you're talking about.
Sure. So if you kind of walk through the system, the collection system itself provides primary treatment. So a septic tank provides primary treatment, and basically primary treatment is just reducing solids in the wastewater, reducing the BOD down to some level. It's not. So then when you go to secondary treatment, we start talking about very low levels. We're actually typically adding aeration, like I said. So instead of having that 140 BOD that's coming out of your septic tank, that we're actually using aeration to take that BOD down to a very low number, usually less than 10. We target 5 milligrams per liter. Tertiary treatment, now you're getting into this next level where you're removing nutrients, where you're disinfecting. So when you see our plants that are designed for tertiary treatment, that means that they're the full meal deal. They're adding now not just aeration, they're adding other infrastructure to actually take nutrients out to disinfect, and disinfection can be done with UV or chlorine or something like that. So you're just really just talking about the different levels of what a treatment plant can do.
Are the aerobic systems that
Yes.
I think 12 of them on Puuko, are they secondary or?
They would be considered secondary, yes. Yeah, but it's just, again, it's I call them blowers and boxes. So essentially you have a tank, you put a blower above it, you pump air into it. That's what an ATU is. And so, as I said, when we start talking about the organic strength, air takes out organic strength. That's how organics are reduced. So yes, ATUs reduce organics, and they're going to convert. So what happens first? So I can't convert ammonia to nitrate until all of those organics get removed. So that BOD number that I was talking about, you actually have to get it down below 10 milligrams per liter before you can actually start doing that conversion from ammonia to nitrate. So an ATU in itself might not even be doing that. It really depends on how much solids are in it and how big it is. And so let's say now it actually does do that. There's other inhibiting factors that actually would also stop you from converting ammonia to nitrate. You need alkalinity to do that. You have to have the right temperatures. And then one of the difficulties in a very small scale system is you don't have an operator there adjusting everything. You're just relying on this blower being on all the time. And so that's why, you know, if your end goal is to actually get all of those nutrients, all of that nitrate out of there, the answer is usually to go to somewhere where you can actually do it as a community.
So on your package plant, since a lot of the houses around here are summer homes.
Yeah.
Do you feel you're going to have enough nutrient load for the anoxic renutrification to get down to the low nitrate level?
It's like you almost sound like you have a wastewater background.
No,
That's
I
a
know
great
nothing.
question.
I know nothing.
So I'll try to frame that way. So yeah, so first we can address what are the impacts of seasonal fluctuation and flow. So in aerobic systems, that can be problematic. If you don't have enough flow coming in, it doesn't have enough organics in there to actually maintain the process. The tanks are too big. And usually the way around that is they create multiple trains so that they can shut parts of the plant off and guide the flow into a smaller portion of the plant. Now, the other difficulty in that is, and I think this is what you were saying, and it's true, is to do that step where you're converting ammonia to nitrate, I need what they refer to as carbon. And guess where the carbon comes from? The carbon is that BOD that I talked about. So what happens, and it's not just caused by seasonal issues, is I have to get rid of all that BOD to actually nitrify. And this is always the catch, is that when I denitrify, guess what? I need carbon all of a sudden, and I've already got rid of it all to start the process. So most plants that have a really low requirement for that total nitrogen or nitrate, they actually add carbon back in. So that's usually in the form of like glycerin. Some are methanol, but I don't recommend methanol because obviously it goes boom. So usually it's glycerin, and they'll actually dose that glycerin back in to that tank that doesn't have any oxygen in it to actually complete that denitrification process. So again, scale matters. That's a very complicated system that requires fairly complicated controls. You can't scale that down to a single home. You need some scale to actually make that work. Yeah.
I guess the question is, on a package plant you would put here as opposed to the lagoon, you would need that other level of anoxic feeds.
Absolutely. Yes. Yep. Yeah, there's certainly, and actually it's one of the problems that we see nationally is we're seeing really restrictive limits showing up in really obscure places. And I think if I was a lobbyist, I'd be going to the decision makers and saying, you guys need to stop this, because the complexity of the plants, there's not operators that can actually operate these plants. And the burden comes back on a company like Orenco. We're out there trying our best. Like we build the system, and then we're constantly training operators ourselves because it's our name that's on the system. So when I say we have a post asset division, that's what they're doing, is they're actually working with people that operate our systems, because there's no other avenue to get these people up to speed on how to actually do it. They're used to having blowers and boxes. And this is way more complicated than a blower in a box. Yes.
I put a state-of-the-art Orenco system in. I put a state-of-the-art Orenco system in about 12 years ago, and it's functioned really well. I'm pleased with it. If I want to take that further, nitrogenation and the infrared, you're saying I really can't do that.
So depending on what system you have of ours, it already does some of that possibly. So yes, you may not know the question if you have an RT or an AX20. But what happens is you have essentially what I showed you. I showed you a big version.
I have all of that.
You have a small version that's just sized for your house. So that media acts just like a blower in a box. That provides aeration. So we are converting your ammonia to nitrate, just like an ATU will, but we're doing it without blowers, right? You have no blowers on your system. It's just a recirculating pump. When it goes into that system, we can recirculate that flow back into your septic tank. And when we do that, guess what's in your septic tank? There's no air. It's what I refer to as an anoxic environment. It will denitrify, and we can get that 60% removal efficiency all the time. If you wanted to get that down to a 10 total nitrogen, we would actually have to add a vessel in behind it. And in the big systems, we use a technology called MBBRs. And an MBBR, basically, that's the way I describe it, is it has suspended media floating around in it that becomes a place for the microorganisms attached to. But again, we maintain it in this anoxic environment and we add carbon back in. It's a little hard to scale it down to your scale. We do that though. We do, on large homes, we've done custom units where we actually have all of that in there, but it's really expensive at that scale.
Mike, can I ask a question?
Sure.
Can you tell us about your Orenco's experience in Hawaii? And if we wanted to go with one of your treatment systems, who would run it for us?
So that's a great question. And so the question is, who would operate the system? So a couple of things. So we have business partners in Hawaii that actually already do sell our equipment at the residential level. That's how you got a system, is that we have, right now we have 2, we refer them as residential dealers that sell our products. One of those dealers is actually already said that they have capacity to actually support a municipal type project. So what that means is that Orenco would do all the heavy lifting technically, but the logistics on the ground as far as coordinating installations and assembling those tanks and making them available, we already have that in place, that we'd have a partner here to do that. And we've been doing work in Hawaii for a long time. I will say at the residential level, states that allow ATUs, if you're just purely buying a system on price, the same thing applies. ATUs are going to be much cheaper than our systems for a residential system. We're going to be much lower to operate because we don't have blowers. And that's, unfortunately, that's what our dealers always have to overcome at the residential level, is they have to sell that value to their customers. But we've been doing it here for years. On the operator side, so we do operator training. Whenever we sell a system, we actually come in, we do the operator training. So we certify that we've trained them and they operate the system. We provide ongoing support if they have any questions. All of our systems are remotely monitored. So what that means is that the operator doesn't have to be there. They can go on their laptop and see what's going on. If they have a problem, they phone Orenco and we actually go on their system, and our people will actually dial into the panels, start looking at their records as well and say, hey, you need to adjust this, this, and this. So we actually always have remote capability to assist in that way. The other thing that we do is if they start to get into trouble, let's say that they're not getting, this is a 10 total nitrogen system and they're getting 15. They phone us, they ask for assistance. We say, well, here's where you need to pull samples, send us your samples. We provide technical assistance to try to get them back into line and tell them why they're not getting that number.
For a long time. They're not very comfortable. So let's try to wrap this up in the next 5 minutes. Does anyone else have any other questions?
So I have one more question on the inflow into your receiver tank. How do you keep it a laminar flow and not a turbulent flow to bring up the sludge from the bottom?
So in the primary tank, you can almost mimic our large tanks like the small tank. So it comes into a T. It's not just an open discharge right away. So it actually comes in at the midpoint of the tank in a gradual release. The tanks are really big too. So we're not causing a lot of turbulence in there. And it's not enough to cause sludge to shift unless you had I&I. I mean, if you had an I&I event, that's a big issue. But in normal operation, not a big deal. If in large systems, a lot of times what we'll do is we'll actually put an EQ tank out in front as well. But our system actually softens those peak flows naturally. So unlike a gravity system where the peak flow can be, 4 times average daily flow normally, and then during a rain event, it can be 10 times normal flow. That would be a concern going into a primary tank. But in our systems, it's usually only about double. Because we have these tanks all throughout the collection system that actually softens down that peak flow. So we don't see that abrupt discharge or that something that causes turbulence in there. You're sure you're not a wastewater guy?
Do you need a job here in Puerto? Yeah.
Talk a little bit about how the other developments that you've worked on are typically financed.
Good question. So the question is what have we seen? So again, we do these all over the country. So a lot of our projects are usually funded through USDA or Clean Water SRF funds, a large proportion of them. The difficulty in that is time, because it takes time to go through those processes to get that money. A lot of communities go through that painful process because they're eligible for some level of grant money. And that's typically the forgivable portions of those loans or grants is based on median household income and where you are to state averages. And that formula for a lot of our clients works in their benefit. Sometimes it doesn't. So that's, to me, if it pivots from there and into more of a time element, which may be the case here, then there's usually other ways. Appropriations are much faster. So we have a lot of projects that don't go through that red tape. They're simply appropriated by the state, where they basically put it into some legislation and say, we're financing this project. And that's the perfect world, because there's no strings attached. It's simply an appropriation of money to get it done. We also see private money go into some of these projects. We have people knocking on our door all the time looking for models to actually start to integrate more private money into financing. The benefit to that is they tell us that the private model could happen in as little as 6 months to make money available. The problem with that is it's a higher interest rate, and certainly there's no grant money there. But my experience, the expected return on private money isn't what it used to be, because they're leveraging. I mean, we have one company that's leveraging bonds they're buying in Europe and coming up with actually pretty good terms. So there is companies out there. I mean, and the reason I think that this is materializing is I think a lot of private financing companies are looking at the water space and realize there's this massive need, and everybody's trying to come up with a model on how this works. I know there's one that's working here in Hawaii now, Sustainability Partners, that keeps asking. So that might be something to bring one of those to the table and say, okay, here's the cost. What can you do on the private side to make this work? We have a partner on the mainland. They actually originate out of the broadband company or side of the business. So they've been financing fiber projects forever. They came to us and they saw the similarities between what we're doing and what fiber does. And so they're working with private developers. They're actually picking up part of the capital cost in exchange for running fiber in the development, and they're subsidizing the wastewater cost. And that's an interesting one. So there's a whole bunch of different models, even within a county. And I think I don't want to pick on the county, but everywhere I've ever worked, the county is the lead agency and has really come to the table with ideas. And I know the county that I work for, we actually borrowed money from our enterprise fund, the landfill, because the landfill had been putting money away for years for the eventuality of expanding the landfill. And they had, I don't know how many millions of dollars in the bank. We actually borrowed money from the landfill to kick off projects and then put it back after we generated revenue to pay it back. I did a program in Florida. I used a revolving fund. I put all the lines in with a revolving fund. I had a connection fee that actually mirrored the cost of fronting the property. And when people connected to the system, I took that component, put it back in the revolving fund, and used it for the next project. So you can get creative. I love getting creative.
Okay, this is my last comment. This is the most reasonable approach I've ever seen. So I appreciate that. You've done a good job. The other thing about non-point nutrient source is I don't think we've done a lot of outreach to make sure that we're not fertilizing our lawns. Mm-hmm. We're keeping our leaf litter picked up, because all those things contribute to the nutrient load on the beach. And so anyway.
So there's a lot of examples. I mean, so other areas that we see nutrient impacts, in like Florida. I mean, I lived in Florida for 28 years, and nutrient loading was a big issue there. I mean, we saw grasslands in our estuary dying. You know, they're making the same connections. And so there's several communities in Florida that have actually taken that next step, where they've adopted local ordinances that says, here's the maximum application rates for fertilizers, and this is all you can sell at Home Depot or Lowe's. And it's worked. I mean, I don't know how effective it is on the end result, but I'm saying that they've been able to regulate at the level of flows and targets and what they're selling. So there is examples out there to address kind of some of the stuff you're suggesting there.
Thank you so much.
You're
Mike.
welcome.
Round of applause.
The last thing you might want to, if you go to our website, you will be surprised how much information there is there. It is loaded with case studies. It's loaded with, we even have landing pages on sea level rise and all kinds of stuff on there you wouldn't expect to find. So if we have webinars you can attend if you really want to educate yourself. I get suckered into podcasts all the time. So we got all kinds of podcasts on there, but you might find it kind of interesting to go there and see what we're actually putting on.
Thank you so much, Mike. That was great, right? All righty. Thank you all for coming. I wish the pews were softer. I see you all wiggling around. June 20th is our next one of these. Dr. Greg Asner, who is an expert in coral reefs and marine biology and studying wastewater on reefs, will be here to answer all of our tough questions. That meeting starts at 6 p.m., but we'll remind you. So thank you.
I would suggest everybody. It's fascinating what he does.
Yeah, he's really good. Okay, thank you everyone very, very much.
Dinner reservation at 7:45.
What time is it now? See, I never know what time it is.
So-